Okay, good afternoon again. First, I'd like to present a question. I'm Miika Valtonen from Remion, yeah, but is there someone who wasn't here in the morning? So everyone was and probably saw the first presentation, so may refer to that. But yes, Valtteri may present himself at this point if you want.
Okay, hello all. I'm Valtteri Peltoranta from Konecranes, Senior Reliability Engineer, and I came to here to tell you about the company perspective of this flow-based AI. I can actually start to tell you about the background, why this topic was interesting for both of us, Konecranes and Remion. So Konecranes provides brake monitoring for our cranes. Brakes are critical part of cranes because they hold the load when the crane is not moving. So of course we don't want that the load drops, and they also are important for the total functionality of the crane. So the brake monitoring device provides this continuous remote monitoring for electromagnetic disc brakes. So we monitor the opening current of the disc brake, and with that information we can estimate and also we collect the fault information from the brake control signals. So why we do this? We want to reduce the risk of any functional problems and the load drops. And then we also want to estimate how the brake is wearing out, and if there is some kind of control problems. And by doing this we can plan the maintenance better and also avoid any unnecessary inspections. And we wanted to improve this solution even further by applying these flow-based AI methods. So how the digital twin comes into the picture? The digital twin should know what is the state of itself. So for example, if human is feeling that his or her stomach is hurting, it's information about the condition, and in the same way digital twin should know if there is some kind of problem in the condition and tell that information to the people who can help in the situation. So when we have the digital twin of the Ilmatar crane and we have the brake monitoring there, we can give understandable observations to the service personnel and to the operators that what is going on in the brake system and what we can estimate how it will behave in the future. So we wanted to have these AI-based methods to have more proactive observations about the system. And now Miika will tell more about the technology solutions, what is actually done for the brake monitoring signals and how we analyze them in more advanced way.
Thank you, Valtteri. So given this background, we proposed a technical solution in this project for this and created a prototype. And this is the regatta flow I mentioned already in the morning, and let's look into that in more detail now. So we created a brake monitoring flow like this so that we could analyze the brake data, and there are several sections we can see from this flow. First, there's the data ingestion section, from which we see this couple of purple nodes. Then there's the data selection. We select the data from the data lake where it is ingested first into, and then we have the signal processing section, and finally the fuzzy inference, the AI, artificial intelligence section, in which we do the inference with the data. So let's look closer at these parts. So first, the data ingestion. We have there multiple topics that use MQTT as the protocol. We use to ingest the data from the crane that we are analyzing. And in MQTT we have a topic structure which we are using so that we have there the source. So that may be a crane 1 or crane 2, any asset. And then there's the signal behind the slash. And in the payload we transfer the timestamp and the value of the signal to the data lake. And there's time series data stored there, so you can retrieve that to your eyes as well on any IoT platform, for example. And there are SQL queries also that are supported, so you can query that for data analytic purposes. Well, from the data lake we can select the data for further processing, and we can subscribe to any updates that are happening within the lake so that they can be processed further. And we use again the MQTT topic for this data selection. And all new notifications that are coming to the data lake through the MQTT channels are then propagated to the attached nodes in the signal processing section. And here you can see some of the examples of the nodes that are included in this prototype flow. And first we have here the time aggregation type of node that temporarily aggregates the data to a higher level, for example to a minute time period. And there are different aggregation functions we can use: standard deviation, average, median, maximum, and so on. Also we can aggregate several signals together. For example, we have here several faults coming to one single node where we just count the number of nodes. Or then we can transform functions, use transform functions to recalculate the data, for example, from cumulative values to incremental values. And going on with math nodes, we can apply some basic mathematical functions like multiplying, division, and some more advanced ones. And with this signal processing, we get the data to a point where we can apply the fuzzy inference to the data, which is the actual point of this exercise we're doing and the prototype we're evaluating here. So what is the fuzzy inference in hand we're talking about? Fuzzy inference is a method where we want to have linguistic values of data. We want to understand the meaning of the data. And here you can see a distribution of data as blue bars, and we apply an algorithm to automatically set some linguistic variables that describe how the data fits into those categories. Here we have a few examples. We have excellent, good, degrading, warn, and critical terms that are used with the data. And like humans, we don't know if it's cold or hot. Someone say it's warm, but for someone 23 degrees is warm, for someone it's hot. So it depends also on the person. So it might be somewhat subjective, and so it might be different for different assets as well. So we need to combine these terms specifically for some fleet or asset, depending on what we want to use the terminology for. So having these linguistic terms, we can then generate them from the automatically or manually, as said, from the data. And then we can use them for easy interpretation of the values that we are outputting from the inference section. And using this fuzzy inference section here in the flow, we can do causal reasoning where we input some values from the flow, and we have used here some indices from 0 to 100% in the flow, and the associated linguistic terms are then shown there above those nodes. and we see that the brake lining wear is changing the brake mechanical health, and then again it changes the brake system health altogether, and there are other inputs there as well. And each of these nodes has an if-then section that's using these linguistic terms for calculation using the fuzzy logic rules. And here you can see some examples of the rules. For example, if the brake mechanical health is non-functional, then the brake system health will be non-functional as well. And there's BMU health, so the unit health itself that's monitoring the data, that has the same type of rules there as well. So using this type of inference, we get some benefits. And here's some examples of the benefits. We can interpret the data. Here we have inputted some data from a test train there for 2 months of data. And then there are 2 signals plotted here in the figure. And we see the brake system health and the brake mechanical health from that tree. And we see how they change. And now we can use these linguistic terms we have defined to see that there's some good values most of the time, but it's interpretable to critical value 2 times in this 2-month period. So that's one benefit. We can understand the data meaning. Then also, if we see some health declarations on the brake system health there, for example 57% on the right, then we see there's some problem going down the road to the left, so we can find that the root cause of the problem. So finally, the system health has gone down because the brake is wearing down very fast. So we can see the state change already at that point and figure out what's wrong with the brake. And Valtteri may go on and explain more about how this applies to Konecranes and their brake monitoring than in practice.
Thank you, Miika. Like said, what this gives to us is that the digital twin actually makes a lot of the analysis work that's done usually by human who should utilize the information. And by using this method, we get this human-like observation, what is going on in the physical product. So we want to have these easily interpretable notices and warnings that are sent to the people, the service, who then make the actions to correct the situation, to make the adjustments to the brake and do the possible service actions. So an example from the Ilmatar crane would be that if it's in heavy use, we would in a proactive way notice that, okay, now for some reason the brake lining is wearing faster than it should. So we are not actually waiting that the symptoms cause problems so that the brake lining would be already worn out, but we are already estimating that, okay, there is something going on based on the signals and based on this analysis, and then we will make the actions well beforehand. And this gives us a better way of doing actually it should say here predictive maintenance. For some reason there's the old word preventive, but we are aiming for the predictive maintenance purposes. And another example would be that if there's a occurring fault in the control signals, the digital twin would already observe its own condition that, hey, I have a lot of these fault signals during the last 24 hours, and this should then give the action for the service that, hey, you should now inspect the brake controls and the boost time, for example. So this is more advanced way of utilizing the condition monitoring data and having the information in a human-like observations. Thank you, that was our presentation, and I want to also thank everyone who stayed for this afternoon session to hear these later presentations. Thank you.
Thank you.
Thank you, Miika and Valtteri. So, time for questions. Now we are ahead of schedule. That's surprising. So there's one in the back at least.
Hello, I'm Tuhin from Peltoranta University Technology. My question is, from the top node on the right, how do you identify that which is the root cause, or how do you connect those nodes back to the root cause of the problem? Is it some sort of analytical calculation, or what is the basis of that connection? Thank you.
Yes, good question. The state of those nodes to the left from the root node on the right, they change also. So we can just evaluate the index number or the linguistic term shown there. And we can see that the term very fast is bad. So we can just look at the node's result there. So it's evaluated the whole tree all the time. And all those nodes have states that are then propagated to the right along the calculation.
One question from my side. So how adaptive is this analysis or algorithm if you want to add more data points to the analysis or this AI flow? So for example, some vibrational data of the building or whatever. Is it easy or do you have to teach the system all over again and again with new data points?
Well, if you're asking technically, Valtteri may answer like if its purpose is useful, but then you can just drag and drop new signal nodes to the flow and attach them to some new calculation nodes, so it's easy.
Yeah, of course, from company perspective, one challenge is that if we have some new data, we always have to know what the changes in the signals mean, and that's something that we still have to teach for the system. So we have to know the different conditions of the signals and tell to the system that these are the limits that we can use, and if something happens, then this is the observation based on that. So that is, of course, sometimes time consuming and needs some human analysis before we can teach it to the system.
Okay, thanks. Next question is, can you get rid of some data points, maybe using AI? Because maybe you can get the same analysis results with less data points. Have you figured out that possibility?
Well, no, we haven't looked into that really yet, into minimizing the number of inputs. We can do it, of course, in our brain when we look at the data, but automation for that hasn't been implemented yet. It's easy to see from the flow when you analyze it visually, but then there's no automation for that yet.
Okay, thank you.
Thank you.